There are senses that animals possess that humans do not, and we're going to look at two of them here, infrared and ultraviolet. So let's start with infrared. There is the visible light spectrum, and way down in that range is infrared, which is outside of our range. Our range goes right above the infrared to this line right over here, because ultraviolet is in this area, and we do not sense that either. So let's start by looking at infrared receptors in snakes.
Talk about a shot in the dark. But even with its vision blocked, this snake strikes its prey with pinpoint precision.
This blindfolded snake can strike perfectly accurately based on its thermal sensation, its ability to detect warm objects in its environment. It is literally seeing heat.
With support from the National Science Foundation, Florida tech biologist Michael Grace and his team carefully study these reptiles' infrared sensors.
This ball python, like most boas and pythons, has an array of these infrared sensory organs called pit organs right around the mouth. So their brains have an image of the visible world and an image of the thermal world, so they see both light and heat together at the same time.
Now, the California ground squirrel, interesting animal, and interesting in terms of how it has adapted to one of its main predators, rattlesnakes. The thing about the California ground squirrel is they can actually produce infrared heat in their tail as a defense.
The common ground squirrel has evolved superpower defenses to protect the colony at this moment of danger. The heart of the squirrel's strategy is deception, looking and behaving like something else. And why it works has everything to do with how its opponent sees the world. A distinguishing trait shared by a group of venomous vipers around the world is the heat-detecting organ located on the sides of their heads. They're known as the loreal pits, external openings to a pair of extremely sensitive heat registers that help the snake judge the location and the size of warm-blooded prey. Working like a pair of rudimentary eyes, heat pits enable a snake to discern something warmer by only 0.003 of a degree from the surrounding temperature. But somehow, the squirrels have learned all this. Or at least enough to know how to use the rattler's own heat detection against it. Faced with a rattlesnake, a squirrel begins frantically flicking its tail. This isn't panic. It's actually flooding the tail with blood, making it nearly as hot as the rest of its body to increase the size of its own heat profile. The snake is thrown on the defensive. Other squirrels join in, chirping out alarm calls to warn the rest of the colony.
So why would the snake go on the defensive? Well, I'm not sure we really know the answer to that, but one suggestion is that it makes the squirrel look significantly larger and not something that the snake would want to go after, but something that might actually harm the snake, at least as the snake sees it with its infrared receptors. So here's some more work that's been done with the California ground squirrel. And we have two species of snake, a gopher snake that has no infrared sense and the rattlesnake that does, as we just saw in the video. So it turns out that if these snakes are approaching the California ground squirrel, notice over on the left that the squirrel does not produce any kind of infrared heat in its tail when it's confronted by the gopher snake, because the gopher snake can't sense it in the first place. Somehow the squirrel quote-unquote knows that. Whereas over on the right, we see what we saw in the last video, where there's a considerable amount of infrared heat in the squirrel's tail when confronted with the rattlesnake. And it's wagging its tail around. And robotic squirrels were used in an experiment to actually look at rattlesnake reactions to the tail display with infrared heat versus no infrared heat. Now, the videos I have here are not robots. They're just live squirrels. I don't have videos of the robots that were used in this particular study. So that's not robotic. That's live. Anyway, no infrared in the tail. Again, they were using robotic squirrels where they controlled infrared heat. And the rattlesnake remains very aggressive. But then when the robotic squirrel, and again, that's a live squirrel down there, but when the robotic squirrel produced infrared heat in the tail, that is when the rattlesnake switched to defensive behavior. Now, vampire bats also have an infrared sense. They have these special sensors near their nose. And fruit bats, for example, don't. So these receptors are not even found in fruit bats because they don't feed on blood, whereas vampire bats do. So what these infrared sensors enable the bat to do is to locate areas of the body where blood is particularly close to the skin on animals they want to prey on. Okay, that was infrared. Let's look at ultraviolet. So we're at the opposite end of the spectrum. Again, we do not sense ultraviolet, whereas a lot of non-human animals do. And so it turns out that ultraviolet plays a large role in communication, especially with respect to mate choice. In a variety of birds, it's been well documented in zebra finches, starlings, and blue tits. So for example, if we leave the male zebra finch alone so that it is producing ultraviolet, even though we can't see it, the male would become is highly preferred by females when courted by the males. But if we introduce an ultraviolet filter to filter out the ultraviolet light between the male and the female, even though the male is actively courting the female, he suddenly becomes less preferred. So ultraviolet coloration is something that does play an important role in female choice of mate. So here we have some male blue tits. Now, over on the left, we have on top the bird as viewed in visible light, the way we would see it, and then only in ultraviolet light, the way that a female blue tit would see it. And you can see that the top of the head is highly reflective. Now, over on the right, we are inserting an ultraviolet light filter, and you can see in visible light, there's really no changes to the way the blue tit appears. But down below that, with the filter in place, you can see that the crown is not reflective anymore. So if given a choice between the male that is displaying ultraviolet light with the highly reflective crown and the one that is not because it's being filtered out, you can see that females prefer the highly reflective crowned male, but not the one where the crown is no longer reflective. And it turns out, this is kind of interesting, that female blue tits also produce ultraviolet light. They have ultraviolet reflective crowns as well. So there's no sexual dimorphism here in terms of the ultraviolet reflectance of the crowns. So the greater the ultraviolet reflectance, it turns out that the greater the number of chicks that will be fledged and the lower the level of stress hormones. So that's an interesting correlation between the level of ultraviolet reflectance in the females and how successful they are at nesting and producing offspring successfully, as well as in the level of their stress hormones. Now here's an African lizard, and its dewlap, the area under the chin that it uses in aggressive displays as well as in courtship displays, contains a lot of ultraviolet reflectance. Of course, we would not see that because we don't see ultraviolet. We just see all the regular colors. It's a very colorful lizard. So the name of the species is the Augrabi's flat lizard, and its agonistic display, its aggressive display, is to flash its ultraviolet dewlap at other males. So the greater the amount of ultraviolet on the dewlap, the greater the fighting ability of that male. If you block it with sunscreen, so there's no ultraviolet reflectance showing through, the male will lose his dominance status. So it plays a really important role. This is a parakeet. In Britain, they're called budgerigars or something like that. I'm probably mispronouncing it, but they also just call them budgies for short. Okay, this is the way we see the parakeet. This is the way another parakeet sees the parakeet. And you can see there's a lot of ultraviolet reflectance.
Blue tits, in our eyes, are one of the more colourful of our garden birds. But in ultraviolet, they're much brighter still. Their crests are particularly vivid and much brighter in males than females. So to them, these sexes look very different, whereas to us, blue tits all look the same. We would all, I imagine, think that budgerigars are unusually colourful birds, but ultraviolet radically changes the character of their costume. Their feet glow, and the spots on their cheeks, which are not particularly prominent to our eyes, positively blaze. Indeed, a budgerigar's full dress uniform is dramatic in the extreme.
So animals are seeing things that we cannot see. Totally different view of the world. Jumping spiders also have ultraviolet light, both the male and the female. So the top two photos show the male on the front and the female from the front. And then the bottom two photos, the male as viewed from the top and the female as viewed from the top. Now, if we look at them under ultraviolet light, you can see that they both have ultraviolet reflectance, but very different patterns. So there is sexual dimorphism in their ultraviolet reflectance. If you filter that out, guess what? Decreased courtship by both sexes. So as is the case in birds, ultraviolet light is playing a huge role in courtship behavior and successful mating. And butterflies also have ultraviolet reflectance.
The wings of African satarid butterflies are decorated with constellations of eye spots. They're arranged in patterns unique to each species. Yale biologist Antonia Montero studies the evolution of these patterns.
They seem to use these eye spots to communicate with each other during courtship. They seem to be very important in terms of female choice.
Scientists have assumed that females are drawn to males whose eye spots have the largest white pupils. Antonia has come up with a different theory. She has observed that females respond only to the eye spots on the upper sides of the male's wings. The eye spots reflect ultraviolet light. Light in the ultraviolet spectrum is invisible to humans, but many other animals are able to see it and use it for sexual displays. With a special UV camera, we can get an idea of what the world looks like to a satarid butterfly. Those reflective eye spots catch a female's eye, especially when the male flutters his wings during courtship.
Look, a male trying to court with a female.
Antonia wonders if females use this ultraviolet flashing as a way of selecting their mates. To test the idea, she'll block the reflections with a little paint. Carefully separating a male's wings, she dabs a transparent solution on his upper eye spots. It's a plant extract that works like sunblock, stopping the passage of UV rays. In normal light, the eye spots stay white, but under ultraviolet light, they disappear. Antonia places two males in the presence of a single female. One male has his eye spots painted over, The other retains his normal gleam. Jamming his sexual signals by blocking the reflections effectively puts an end to a male's chances of mating. The female just isn't interested. As for the male whose eye spots continue to shine, his wings give him the winning edge. So, among satyrid butterflies, it's not the size of the spots that matters, it's their sparkle. That's the signal the females are looking for, even if it's invisible to us.
What's especially interesting to me about that is that even though the white is still there, the female doesn't care. She's looking for the ultraviolet reflectance. Infrared and ultraviolet, two senses that are not sensed by us but that play a huge role in other species.